Here we discuss the chemical shift of NMR. We have already seen the resonance condition of the protons, so which is given by h nu is equal to the energy difference between these levels, which is Gn mu n into B0. Suppose B0 is the applied magnetic field. So if we use the approximation I is equal to root of I into I plus 1, we also get that the energy separation between the proton spin up and proton spin down configuration is given by delta I is equal to mu B0 by I. So for protons I is equal to half, so and therefore the energy separation is 2 mu B0. So we have already derived this and this. So we can either use this equation h nu equal to Gn mu n B0 or h nu is equal to 2 mu B0 or mu B0 by I in the case of protons. So from this equation it is clear that all the protons absorb energy at the same magnetic field. But experimentally this is not true. The resonance, either the resonant frequency or resonant magnetic field. So we have already seen that in the NMR experiment we can either change the frequency or we can change the applied magnetic field. So in either conditions the resonance will not be same for all the protons. The resonance depends on the chemical environment or the chemical surrounding of the proton, and the shift associated with this is generally called the chemical shift. For example, the spectrum of acetaldehyde, which is CH3CHO, so we have seen that in this case there are 4 protons. So but when we observe the spectrum of acetaldehyde, we can see that there are 2 intensity peaks. There are 2 lines and their intensity ratio is 1:3. So if we vary the magnetic field here, so the intensity of the first one and second one are in the ratio 1:3. So that means the absorption magnetic field or the resonant absorption of the proton in CHO is different from the proton in CH3. So similarly, if we observe the NMR spectrum of ethanol, which is CH3CH2OH, we can see that there are 3 peaks. So there are 3 types of protons here, one in the OH group and other in the CH group and other in the CH3 group. And for this we can see that there are 3 lines having intensity in the ratio 1:2:3. And in this figure, this corresponds to CHO proton and this corresponds to CH3 proton. So the intensity is proportional to the number of protons present in that group, and this corresponds to OH group, and this corresponds to CH2 group, and this corresponds to CH3 group. So why this is happening? So the reason is that the moving electrons in a molecule constitute a current. So the electrons are revolving around the nuclei in circular path, so they form a magnetic dipole. So they constitute a current. So this effective current within the molecule produces a secondary magnetic field, so which opposes the applied magnetic field. So due to the revolution of the electron, there is a magnetic field produced in the opposite direction as that of the applied magnetic field. These are called secondary magnetic fields, and that acts in a direction opposite to the externally applied magnetic field B0. So, the nucleus which is placed here will have an effective field which is less than the applied magnetic field. So, we can say that the nucleus is being screened by the surrounding electrons. So, the effective magnetic field will be less than the applied magnetic field, and that is equal to B0 minus this magnetic field due to the electrons. And we can see that this magnetic field due to the electrons is equal to sigma times the applied magnetic field, where sigma is the dimensionless constant called the screening constant or shielding parameter. Screening constant or screening parameter or shielding constant or shielding parameter. So, this is equal to sigma times B0, and the effective magnetic field is B0 into 1 minus sigma. So, we can see that due to the shielding of the electrons around the nucleus, the effective magnetic field decreases. So, the effective magnetic field is applied magnetic field multiplied by 1 minus sigma. 1 minus sigma is a quantity less than 1, and when we multiply it B0, it is less than B0. So, the nucleus will find itself in a field which is less than the applied magnetic field. So, this value of sigma is of the order of 10 to the power minus 15, a very small quantity, and the value of sigma depends on the electron density around the proton. And we can see that in the case of acetaldehyde, there are two types of protons, the proton in the CHO group and the proton in the CH3 group. And the three protons in the CH3 group are equivalent. But in the CHO group, we can say that there is an oxygen which is more electronegative. So, therefore, the oxygen will attract more electrons towards it, and therefore the electron density around the proton in CHO is less than the electron density of the protons in the CH3 combination. So, oxygen is more electronegative, so the electrons tend to accumulate around oxygen, and therefore the electron density around in CHO is less than the electron density around the protons in the CH3 group. So, in the CH3 group, there is no electronegative part. So, the electron density around the proton is sufficiently higher than the electron density around the proton in the CHO group. And therefore, we can say that the screening is more for CH3 group. Because the protons in the CH3 group are surrounded by more number of electrons than the CHO group, and therefore the sigma, the screening constant of CH3 group is greater than the screening constant of CHO group. Or we can say that the shielding effect is smaller in the case of CHO group compared to the screening effect in the CH3 group. So, suppose we have applied a field B0, and the effective magnetic field for CHO proton is greater than the effective magnetic field for the CH3 protons. So, from these equations, we can see that sigma CH is small, B effective is greater in CHO compared to the B effective in CH3, since in CH3 sigma CH3 is high. So suppose we are fixing the frequency in the NMR experiment and changing the magnetic field. Then what will happen is that the proton in the CHO will go to the resonance at a lower magnetic field compared to the proton in the CH3 group. So what is happening is that we know that in the presence of the field, the proton has got two energy levels, and neglecting the screening, we can see that this energy delta E is of the order of 2 mu B0, or we can write mu n Gn B0. So what will happen if there is screening? So then the B0 is replaced by B effective, which is B0 into 1 minus sigma, so which is less than B0. That means the effective separation distance decreases. That means the effective separation distance is now 2 mu B0 into 1 minus sigma, or mu n Gn into B0 into 1 minus sigma. Anyway, it is being decreased by a factor of 1 minus sigma. So suppose we are fixing the frequency and we are varying the magnetic field. So the resonance condition is given by h nu is equal to 2 mu B0 into 1 minus sigma, or h nu is equal to Gn mu n into B0 into 1 minus sigma. So we can see that here the frequency is fixed and B0 is varied, and this effective magnetic field B0 into 1 minus sigma in the CHO group in the acetaldehyde is greater than the B effective of the CH3 group. And therefore we can see that when this is greater, the resonance happens for CHO group at a lower magnetic field compared to the proton in the CH3 group. So here nu is fixed, B is varied, and B0 can be written as h nu divided by 2 mu into 1 minus sigma. So sigma is greater for CH3 group, and 1 minus sigma is greater for the CHO group. So since sigma is greater of CH3 is greater than sigma of CHO, then 1 minus sigma is greater for CHO group, and 1 minus sigma of the CH3 group is lesser. So since this is greater for the CHO group, we can see that B0, the magnetic field at resonance take place, is very small compared to CH3 group. So B0 for CHO group is smaller, and B0 for the CH3 group is higher. And we can see that there are two peaks if we vary the magnetic field, and their intensity ratios according to the number of protons present in it. So 1:3. So this is when B0 is being varied, and this is due to CHO and this is due to CH3. So similarly, in the case of ethanol, sigma of OH group is less than the sigma of CH2 group, which is in turn less than the sigma of CH3 group, and therefore 1 minus sigma for CH3 group is smaller, and therefore 1 minus sigma of CH2 group, which is in turn less than 1 minus sigma of OH group, and therefore the magnetic field at which the resonance happens for OH group is smaller. B0 is smaller for OH group compared to CH3, which is in turn smaller compared to the magnetic field at which resonance take place for CH3, as shown in figure. Now we know that the NMR experiment can be done by changing the frequency also, by keeping the magnetic field constant and by changing the frequency also. But the resonance condition remains the same. H nu is equal to 2 mu b0 into 1 minus sigma, or you can write it as gn mu n b0 into 1 minus sigma. So both are right, and in this equation we have used one approximation, I equal to root of I into I plus 1. So anyway, if b0 is constant and nu is fixed, so nu is equal to then 2 mu b0 into 1 minus sigma by h. So, but in the case of acetaldehyde, we have seen that sigma of CHO is less than sigma of CH3, and therefore 1 minus sigma of CHO is greater than 1 minus sigma of CH3. So we can see that in the case of acetaldehyde, 1 minus sigma is greater for CHO group and 1 minus sigma is lesser for CH3 group, and frequency is smaller for CH3 group. So when we do this for CH3, we can see that nu CH3 is less than nu CHO. So when we vary the frequency, we can see that there are two peaks. The first peak is having maximum intensity and the second peak is having minimum intensity. So this corresponds to CH3 group and this corresponds to CHO group. So this is while we vary the frequency. So when we change frequency, then the positions of CH3 and CHO will be interchanged. So the experiment can be done in any way, but in both cases the effective energy separation between the levels is decreased, and the decrease is more severe in groups having high sigma value. When sigma is high, 1 minus sigma is very small, and therefore since this is proportional to 1 minus sigma, so the separation distance is greatly reduced in the CH3 group compared to CHO group. So this is B0 into 1 minus sigma of CHO for when we keep frequency fixed. So we can see that for CH3 group, the resonance occurs at a lower frequency compared to the CHO group. But when we change the magnetic field, B0 into 1 minus sigma is the effective magnetic field. So the B effective should satisfy the condition H nu is equal to 2 mu B effective, and when sigma is higher, for example for CHO group, B0 will be smaller and vice versa. When sigma is smaller, for example for CHO group, then B0 corresponding to CHO group will be higher. Okay. Now we will give the exact definition for the chemical shift delta. So the chemical shift delta is defined as the shift of the resonance line of a given compound from that of a standard reference sample. So generally the absolute magnitude of the shift is very small. Sigma is generally very small, of the order of 10 to the power minus 5. Generally the sigma of reference should be small. It should be a proton without any surroundings, a bare proton. But in order to get the screening constant of a bare proton is very difficult. So we use some other samples having very small value of sigma. So suppose Br and Bs are the magnetic fields at which the resonance occur for the reference sample and for the given compound or given sample. So the magnetic field at which the resonance occur for the given compound is represented by Bs, and the magnetic field at which the resonance occurs for the reference is called Br. So then we know that Br is equal to B0 into 1 minus sigma r, and sigma r is very small in general, and Bs is equal to B0 into 1 minus sigma s. So now the chemical shift delta is defined as Br minus Bs divided by B0. The shift in magnetic fields divided by the applied magnetic field. So substituting the values, it is B0 into 1 minus sigma r minus B0 into 1 minus sigma s by B0. So B0 terms cancels, and we have 1 minus sigma r minus will be plus sigma s. So this is sigma s minus sigma r. And generally sigma r and sigma s are very small, but sigma r is less than sigma s, and therefore chemical shift is always positive. So since these quantities are very small, a different unit is generally selected. So for expressing chemical shift, which is given by delta is equal to Br, that is the magnetic field of the reference minus magnetic field of the sample divided by B0 into 10 to the power 6 parts per million ppm. Or in terms of frequency, we can write delta equal to nu s minus nu r divided by nu 0, where nu s is the resonance frequency of the sample and nu r is the resonance frequency of the reference. So into 10 to the power 6 again ppm. So here nu s will be greater than nu r, and therefore delta is positive. So generally the reference is selected such that the delta is always positive. That means Br is greater than Bs, or nu s is greater than nu r, or we can say that sigma s, the sample shielding constant, is greater than the reference shielding constant. But in chemistry, a different chemical shift is also used, which is given by tau. So tau is equal to 10 minus delta. So here delta is the chemical shift. The reference compound used for calculating tau or delta is generally tetramethyl silane, which is tetramethyl silane, so which is abbreviated as TMS, tetramethyl silane. So this is a chemically inert compound, and it contains 12 protons which are of the same type. So all the 12 protons are same type, so we get only one intensity peak, and its resonance is sharp and intense. And a very small amount of the reference sample is required in the experiment, since it gives a very intense peak. So we know that from the definition, the value of delta for the tetramethyl silane is sigma s minus sigma r, so which is sigma s is sigma r itself. So tetramethyl silane, the reference and sample are same, so sigma r minus sigma r, which is 0, and therefore tau is 10 minus delta, which is 10 itself. So the tau factor for TMS is 10. And this table gave the chemical shift in tau and delta in ppm units of some compounds, and so this chemical shift represent the screening also. and we can say that these values are used as a powerful tool for structure determination of the compound. Now we discussed the general theory of nuclear screening for an isolated molecule. So this was first given by the scientist Ramsay, but we don't discuss the details of this theory, but we discuss some of the important points. So there are three types of contribution to the screening constant. One is diamagnetic, second one is paramagnetic, and third one is solvent. The diamagnetic one is related to the circulation of the electrons, which generates a magnetic field opposite to the applied field. So this is the one we have discussed now, and therefore there is a shielding of the nucleus by the electrons. So therefore the effective magnetic field decreases. There is a shielding. So in the paramagnetic case, so that is related to the anisotropy of the electron distribution about the atom. So in the paramagnetic case, an additional field is generated, and that is in the same direction as that of the applied field, and that correspond to the de-shielding. So this diamagnetic effect causes shielding, and this shielding is de-shielded by a small extent by the paramagnetic field. So the diamagnetic causes de-shielding, and it is somewhat de-shielded. So that means here the magnetic field develops in the same direction as that of the applied magnetic field. So the effective magnetic field is somewhat de-shielded. Now from the third or the solvent contribution, the chemical shift of the solute molecule depends on the solvent used. So these are the main three contributions to the chemical shift, and there may be other small contributions as well. So the relative magnitude of this each term determines the net contribution. But for protons in an organic molecule, the main contribution is from the diamagnetic. That is the one we have discussed now. There the electrons around the nucleus shield or produces a screening to the effective magnetic field, and therefore the effective magnetic field decreases in the diamagnetic contribution. So this is generally there for the protons in the organic molecules. So in chemistry this term is generally used. And in hydrogen bonded systems like OH, NH, etc., the shielding constant or screening constant is very small. The hydrogen there shares electron with the electronegative elements. So therefore the resonance appears at a lower magnetic field. So the chemical shift in the case of hydrogen bonded molecules can give an information about the strength of the hydrogen bond. But we know that at high temperature the strength of the hydrogen bond decreases, and therefore sigma increases, and therefore the resonance appears at high field. So summarizing, we can say that all the protons will not have same resonant frequency or resonant magnetic field. So the resonance is different due to the different chemical surrounding, or due to the chemical environment, and therefore the separation between the absorption peaks is usually termed as the chemical shift, and we have seen an expression for chemical shift, and the chemical shift is generally associated with the screening. So due to screening, the effective energy difference between the levels in the magnetic field is decreased, and based on the value of the screening constant, different protons will have different absorption points, or different suppose we are varying frequency, then they will have different frequency of absorption, and if we are varying magnetic field, they will have different fields at which the resonance take place. So the points or the positions at which the resonance take place is different when we take the screening into account. And chemical shift is the measure of that screening.